All right. All right, it's time. Welcome, everyone. Today, our guest is Professor Chenyang Xu from MIT, and he's going to give a talk about the very exciting subject about minimizing normalized volume. Please.
Okay, yeah, thank you very much for the invitation. I mean, it's my great pleasure to speak virtually in Sweden to give this talk. So let me start with the definition of normalized volume. Oh, sorry. So we consider the setting is x inside x is a singularity. So this is a local version. So we can just consider this is locally given by a spec R of some local ring. And then we can define the so-called non-commuting link. I mean, this is a fancy word. Just say we consider all the valuations V. These are all the valuations of Kx, which is equal to, of course, the function field of Kr, such that the center of V on X is precisely this small point. So basically, we just look at, so you can think about it like the divider over this point, whose on some bidirectional model whose image is this point, but then there are some other type of valuations as well. So a while ago, work by Lawrence Ein, Latherfield, and Karen Smith, they defined this function of volume on this valuation, which is given by, which is it's possibly zero or some non-negative number. So the way we define it is basically we first define the valuative ideal AK, which is just given by all the functions inside R, such that the VF is at least a K. So this will be a MX primary ideal because because V is always inside this non-commuting link. So from now on, V will always be in this non-commuting link. So then we just define the volume V to be limit of K go to infinity, the length of R divided by AK and the K power to N factorial. N is of course the dimension of X. So I mean, it's not completely trivial to prove such a limit exists, but it's known. So we just define this to be the volume, and as I said, it could be zero. So next thing we want to define another function is called the log discrepancy function. So if you are a bidirectional geometer, this terminology is of course basically something you deal with every day. So the way we define it is basically we have 3 steps to define for 3 different generalizations of 3 different level of valuations. So the first one is if V is given by some divider, so it's some divider over this point, we just define this to be multiplicity E K Y X plus 1. Oh, sorry, from now on I have to make assumption that X inside X is a Kawamata log terminal singularity. The volume can be defined for any singularity, but from now on, I have to make this assumption. It's Kawamata log terminal. So particularly the Kx, you can pull back to any bidirectional model over that. And now if we have a model such that E is inside this Y mapped to a point, then we just define the AXV to be the multiplicity of the relative canonical bundle plus 1. I mean, of course, if you are a bidirectional geometer, if you are doing minimal program, you say this very often. So Next level, we want to define the so-called quasi-monomial valuation. I assume not everyone is familiar with this, so let me just define it. So basically, we have some like a simple normal crossing model now, mapped to X. So this is a simple normal crossing model. And now we can think about a bunch of divisor EI intersect at some point and some component of this intersection. And now we look at the generic point. So basically, we have this model. In other words, we have this model, which analytically, locally, it's just simple normal crossing. So then we can define the monomial ideal over this. So if I have a monomial ideal over S eta Z inside YE. So this is called quasi-monomial ideal. So in other words, quasi-monomial ideal is just a monomial ideal. Sorry, monomial valuation. I'm sorry, it's not ideal, valuation. So it's just a monomial valuation over some simple normal crossing model over YZ. So in more concrete terms, this kind of valuation could be given by the number, some number R1. So if I, from here is the intersection of K divisor, I can have a R1 to RK is inside the non, is, maybe I can just assume it's positive. So I have a K positive number. And then, you know, the definition is locally for any function f, around this point, I can just take the expansion using these coordinates. And then, because I just use this alpha 1 to alpha k as a monomial valuation to evaluate on this function. So that's a quasi-monomial valuation. So then under this notation, we define the AXV to be, so maybe I just give a name V alpha. Then in this case, that would be just the sum of alpha I AXEI. So EI is already defined in the first row, and because this monomial valuation, quasi-monomial valuations is just a monomial over this intersection of E1 to EK. So somehow I just linearly expand my definition from the vertex like E1 to EK to this entire convex cone generated by this vertices. So that's the definition of the quasi-monomial one. And then there is more general valuation, which we don't really need. I mean, but let me just write it down. So but if I have a more general one, I just define to be the lim sup of AXVI, such as the VI converge to V. So if V is more general. So because I mean, we know that of course the log discrepancy of a divisor of a divisor valuation of divisor is just some rational number, and then the log discrepancy of the quasi-monomial valuation is some like a positive real number. But because we take the lim sup here, indeed it could be infinite. So this will be inside the 0 infinite. I think this is probably the first definition first appeared in the work of Johnson, Mustada. So, but now I can introduce my key definition. This is the definition by Chili, like about 5 years ago, as said in my introduction, that this is a normalized volume which I define to, I write it as a hat volume of V is equal to AXV power to N to volume of V. So basically I renormalize this volume V by the log discrepancy power to N. Then it's either exercise to show that the volume is actually a rescaling invariant. If I rescale my valuation by some positive number, then the volume doesn't change. Actually, you easily see that if I rescale my valuation, the AX goes by linear, and the volume goes by 1 divided by lambda power to N. So you have lambda power to N in two contributions, and they cancel each other. So and we can also define the volume of the singularity to be the inf of the volume of V for all the V which centered at this point. So this is sometimes we call volume of the singularity. And Chile first showed that this number is actually always larger than 0. So the inf will not be 0. It's actually some positive number. But what's more important is basically Chile, when he defined this volume function, he actually proposed the question to study the millimeter of this function. So although this function is defined in the entire non-commuting link space, we are mostly interested in the millimeter. But the picture is, at least the conjecture picture is finished in some work after the Chile, I know some joint work I did with Chile a few years ago. Basically, conjecture a stable degeneration picture. So that's what I'm going to explain next, what I mean by stable degeneration. So when Chile proposed this, I think most of them are still conjecture, but now many of them are theorem, but there is still one central piece is missed, which I'm going to explain now, what we can prove and what's still missed. So the theorem, the first term is proved by Bloom in 2016. He proved that the function, this normalized volume, indeed has a minimizer. So remember, we originally only defined as the infimum, but now we want to say this actually, this infimum can be achieved by some valuation. So of course, I mean, the non-commuting space of this non-commuting link is quite complicated, and the volume function is not necessarily continuous on that. So somehow this function has a minimizer is something like quite non-trivial. And next is something I proved in last year is that we prove that actually any minimizer is indeed quasi-monomial. So we actually know that no examples that the minimizer is not necessarily divisorial, but what's here is basically says that although it's not a divisorial, but it's not as bad as very general kind of valuation. It's always quasi-monomial. And then a theorem myself and John, and who is here, proved this year is that the minimizer is unique up to rescaling. So of course we know that if V is the minimizer, then any lambda V is, because it's rescaling invariant. But the theorem just say it's indeed unique. And the last part is the conjecture, which this is conjectured by Chili, which says that now if I consider the associated gradient ring. So this is just the ring which is the ideal V quotient by the ideal which all the functions with a value larger than k. Then if I consider all this k inside this phi, here phi is a semi-group of values of V. So if we consider this ring, I call it R0, then this ring is finite generated. So this finite generation is still not known. If the minimizer is a divisor, then we know. But as I said, as we prove it's quasi-monomial. So it's not necessarily divisor. If it's a rational rank 1, it's divisor, but the rational rank could be higher. So then in that case, in general, we don't know it's finite generated. So these are the original conjecture by Chili when she defined this normalized volume. But by now, I think it's 3 parts of the conjecture is solved, but still 1 part is unknown. But so far, you haven't really seen the picture of I mean what I mean by stable yet, because somehow no stable this kind of stability coming out. But that's what I'm going to explain next. So basically, we assume that the finite generation holds. Then what I know? So basically, let me just define the rank of the group generated by phi is R. So R is a semi-group, but if we take all the possible valuations of the entire field, then it's a group. Then it's just isomorphic to Z power to some R. So this is sometimes called the rational rank of the valuation V. And because of the R0 has this gradient structure, then we know that the group G, which is just the torus group with rank R, actually acts on R0, right? I mean, since there is a gradient structure. And we know for any such kind of abstract group, this action G acts on R0, we can take the weight decomposition. So M here is just the home G, GM. So all the possible weight. So if you compare this, decomposition here and this decomposition here, they're slightly different, right? Because in above, the K is inside some phi, is in a semi-value group. But here, below, the W is inside M, which is a weight. So they are connected by the following thing, is that we actually have W mapped to K. So, but what's K? K is essentially just the VW. So here we actually, in other words, maybe I put it the Quasi V. So in other words, we actually have this abstract group W, but we actually put this abstract group inside R. So we actually have this Quasi V is inside the abstract group M inside R. So of course, this is just some co-weight M star tensor R, which I just denoted by NR. So in other words, our decomposition actually give you this gradient ring. In the same time, we actually also basically get a co-weight, which in with real number. So this is CV. And now, so we have the structure X0, which is spec R0 and CV. So what Chili and I proved in 17 is that we first show that the X0 is also KLT. So remember, X is always KLT. But of course, the gradient ring, which is usually a degeneration of this X, even it's finite generated, it could be more singular than X. But we prove X0 is still KLT. And what's more important is X0 with this special co-weight is actually a K semi-stable Fano cone. So let me, before I remind you what I mean by K semi-stable Fano cone, let me just finish what we prove. Basically, we prove conversely, if any V satisfy, this quasi-monomial finite generated, so satisfy the above conditions we prove, and with the property that the associated gradient ring X0 and this CV is K semi-stable, then V is indeed a minimizer. In other words, we actually give a different characterization of the minimizer, at least conjecturally, which is precisely the data of this kind of K semi-stable Fano cone degeneration. So what I think, in some sense, as a minimizer, it's of the normalized volume, it's interesting because it gives you some like invariance associated to the singularity. But geometrically, it's this kind of degeneration picture which is more interesting. That given adding up to KLT singularity, you can actually degenerate to this kind of semi-stable Fano K semi-stable Fano cone singularity. And conjecturally, these two pictures are equivalent to each other. And the missing part is this finite generation part. This is the finite generation part which is still missing. So let me briefly explain what I mean by Fano cone here. So basically, I have this X0, this and also this CV acts on it, right? Remember, this CV is inside the co-weight tensor R. So if this CV is actually a rational, it's not a real, it's irrational, then we know that the CV actually generates a GM inside the G, so which I just write it as CV. You just take the minimal integral vector you generated in CV, and that will give you a C-star group. And any other integral vector on that will be just some power of this. So then I can just take the X0 divided by this GN. So because here I didn't quite explain, because my C is inside of this so-called rib cone. So then this quotient will be actually a projective variety. So this will and because X0 is KLT, this quotient is actually a log Fano pair, which is V delta V, such that this first is KLT at minus V minus delta V example. So this is what I call log Fano pair. And basically the X0, because V is K semi-stable, is basically equivalent to ask this log Fano pair is K semi-stable. So in other words, when KCV is in a rational case, then this K semi-stable question is basically boiled down to some like a more global solution. I think more people are familiar. And in a general case, you can still define Fataki or generalized Fataki invariant for degeneration, for let's say C-star degeneration or GM degeneration of X0 KCV. So you can still do this like same kind of test configuration and the Fataki invariant business like we do in the Fano case. And a theorem by Collins, Ciclidi basically show that if X0 is isolated singularity, then this data X0 CV is K polystable. I mean, since we can define test configuration and the Fataki invariant, of course, we can also define K polystability. But this is equivalent to say that the X0 that meets Sasaki-Einstein metric. So of course, this theorem is just the analog, a generalization of this Yaltown-Townsend conjecture for Fano varieties. And this assumption that the X0 is isolated singularity actually should be removed. But as we know that the Yaltown-Townsend conjecture is for Fano varieties so far is still only improved for the smooth case. So that's why also if you want to generalize to this Sasaki-Einstein case, so far we only know this isolated singularity case. But we actually expect that you can replace this X0 to be isolated singularity to be just by just adding arbitrary KLT singularity. So any questions so far? Okay, so now I give this picture and this conjecture picture, and I told you what we can prove, and then there is still one missing part. But then naturally you might ask why we are interested in this. So I will give you kind of like a 3 application or maybe just like a philosophical picture to explain why we are interested in this. So the first one is basically the so-called Donaldson-Sun conjecture, which is actually proved by Chidi and myself. So in the Donaldson and Sun study, or in general in this like a study of a Einstein metric for Fano variety, for Fano manifolds, we know that if I have X, this is KE manifold, then we take the so-called Gromov-Hausdorff limit. Oh, sorry, this is not X0, XT. So if I have a family of Fano Einstein manifold, we take the Gromov-Hausdorff limit, we can get X0. And this one, we know that, so a priori, this is just a metric space. But now we know proved by Donaldson and Sun in their first paper, building on this so-called zero partial estimate by 10. We know that this X0 is a KLT Fano variety with weak K-stability metric. So X0 itself is not necessarily smooth, but it has this KLT singularity, and it has some like a K-stability metric. So maybe I just write this as omega 0. So this is in Donaldson and Sun's first paper. Then in the second paper, they actually look at the singularity on X0. So this is singularity. And now they look at the ball. Because we have a metric, so we can talk about the ball around this singularity. And now if I look at the metric omega 0, but I kind of room in. So that means I just divide by this Ri square. So and then I let Ri become smaller and smaller. So that's kind of I room in around the singularity. And then they prove that as Ri go to 0, this actually has so in general we know if we have this kind of metric space, if we're rooming around the singularity, then we got the so-called metric tangent cone. C and omega C. And what they prove is that C omega C is algebraic. So C is algebraic, not omega. C is algebraic. And so the first proof C is algebraic. Second, they prove C can be written as maybe as C omega C can be written as a GH limit of an intermediate cone. So basically, there is another cone called W omega W, and then there is a limit here. So, and the third thing they prove is C omega C and W omega W. This do not depend on the choice of CI, of RI. So a priori, when you get this metric tangent cone, usually, you might get different. If you choose different sequence of going to 0, you might have a different limit. But what they prove is the limit is always unique. So this is the statement what they prove. But then they make a conjecture that both W and C. Now, if you forget the metric, you only remember them as a fine cone with some torus action. Then this data only depend on the the arbitrary geometry structure. So, in other words, but not the metric. So, X in X locally is just a arbitrary singularity. And what the conjecture is, although they construct the sub and the some metric stuff, but they just conjecture actually depend on the arbitrary structure, not the metric. So this is what Chenyang and I proved in 17. So basically, we proved that the W first we prove, I mean, they have this like two-step degeneration. First, the singularity degenerates to this W, and then to this CWC. So we first show that basically the W is precisely given by the K semi-stable degeneration of the singularity. So actually, implicitly in Donaldson and Sun's proof, you can already see that the W is given by the degeneration coming from some valuation. And then because W, we can prove W is K semi-stable, then this is precisely coincides with the picture which I described in the first part of my talk. And second, we prove that such degeneration is unique. I mean, this is before the work I did with Zhuang to prove the minimizer is always unique. So up to this point, as we said, we still don't know a minimizer always give you this K semi-stable degeneration picture. But here we already know there is K semi-stable degeneration. So we just want to say that for all such kind of K semi-stable degeneration, it's unique. That was already proved in my work with Chili. So in other words, if we know finite generation, this is then equivalent to what I proved with Zhuang later. But again, we don't know finite generation. So in other words, this two part tells you that the W is unique because it's given by this K semi-stable one, and we know the K semi-stable degeneration is unique. And then later in joint work with Qili, Xiaowei Wang, and myself in 18, we prove that any K polystable Fano cone degeneration of K semi-stable Fano cone is unique. So of course this will imply that the K polystable Fano variety degeneration of K semi-stable Fano variety degeneration is unique, and we prove this two statement in the same time. So basically, we know that this C again because it's a metric tangent cone. You can imagine by this Yelton-Donaldson philosophy, which actually we know we can prove that this give you a K polystable cone, and because W is semi-stable, then you have this unique polystable cone C. So in other words, we actually, I mean, the conjecture, Chilean, this semi-stable degenerate conjecture tells you that for any object KLT singularity, you can uniquely degenerate to some like a K semi-stable Fano cone. And then if you use this theorem, we know it can be uniquely degenerate to this K polystable Fano cone. So I will say that this second step from the K semi-stable degeneration to K polystable degeneration, this uniqueness is somehow well expected. It was somehow well expected, and now it's no. But somehow for given any KLT singularity, we have this kind of unique K semi-stable degeneration. For that's for any object KLT singularity. Before Chili made this list of conjectures, that was actually, I think, hard for biological geometry to imagine. So somehow you really have to have someone with this kind of more complex geometry inside to basically bring up this completely arbitrary geometry picture. But there's a deep K semi-stable stability inside. I mean, it's true for any KLT singularity, but somehow I would say without complex geometers contribution, if for biological geometers who work on KLT singularity a lot, like for the last 40 years, it's very hard for us to basically find out this picture. So the next application of this is something called a finite degree formula. So now let's say if I have a singularity x, it's mapped to some singularity y inside y. Remember, my singularity is always local in the analytic sense. You can think about it as a completion of some like algebra finite type singularity. So if we assume this is a finite, and such that the f upper star ky is equal to kx. So it's cosine. The second condition is sometimes called cosine eta. Then we know. I mean, you can think about this, that I have a Galois group. If I take the Galois closure, then you can think about this as I have a Galois group action on this X, such as the fixed point of any non-trivial element doesn't contain a divider part. So if you have this, then we know it's a consequence of the theorem I prove with Zhuang. Is that if I compare the volume of the downstairs and the volume of upstairs, then they basically differ by this degree. So how do I get this? Basically, we know that we can just think about this as a Galois group action. Then we know, because the minimizer is unique, we know that this group action acts on this minimizer, it will be invariant. So in other words, this minimizer of X will be some like an invariant valuation. Then we know that valuation, you can think about that valuation as the pullback of a valuation on Y. Basically, that's the pullback of its restriction on Y. And then once you have this pullback, it's very easy to check the finite degree formula. So the key is prove that if I have a group action on the X, then the invariant is actually, sorry, the minimizer is actually invariant, and that follows from the uniqueness. So, but this has a corollary that if X inside X is KLT, now if we look at the pi 1, the local pi 1, so we know this is a finite by my work, and which proves the algebra, the finite completion, and the recent work by Lucas Brown. So we know that this, and the topological fundamental group is also finite. This guy, so for any singularity, we can take the take out the X, we take the universal cover, and then we know that the degree is finite. But then you apply this finite degree formula, we know that this is maybe, let me just write it as 2-step. This is equal to the volume of the universal cover divided by the universal, okay, such as the Z divided by Z to X divided by X, sorry, the universal cover. But we know this singularity, we know any singularity, the volume is less than n power to n, n is the dimension. This is proved by Yucheng, Liu, and myself. So we know that this is less or equal to n power to n divided by the volume of the singularity. In other words, the volume of the singularity indeed give you a, I mean, the lower bound of the volume of singularity indeed give you an upper bound of the local fundamental group of the singularity. So we somehow have an effective bound of the local fundamental group by the volume. So if we put it together with a theorem put by Fujita and Yucheng Liu, which says that if X is a K semi-stable Fano variety, then the minus kx power 2n. So the volume of this is less or equal to n plus 1 power 2 divided by n power 2n times the volume of this for any point on x. So if we take this point to be smooth, then we just conclude that the volume of the Fano variety is less than n plus 1 power 2n, because the smooth point, the volume is n power 2n. So that was the original version proved by Fujita, and Yu Chen got this single version. So particularly, we know that if the, this will imply that if the kx has a lower bound, has a lower bound, then, so maybe I should put it this way, plus k semi-stable. So this will imply that the volume has a lower bound. But the volume has a lower bound will imply the local fundamental group has an upper bound. So particularly that will imply the Cartier index has an upper bound. So if you have a Cartier index have an upper bound plus the theorem Hicken, McKernan, and myself prove, this will imply that together will imply all such x is bounded. Maybe I put the implication here to be. In other words, we know that if you have a K semi-stable Fano variety, if the volume has a lower bound, then all such kind of x is bounded. So this actually was originally proved by Chen Jiang, but he used the boundedness by Berka. So the more recent work of this work by Berka on stronger boundedness of Fano varieties, but somehow using this like a more normalized volume approach plus this recent proved uniqueness, we can actually get the boundedness, which only use this like a weaker boundedness without, which Hicken and McKernan and I prove like this is I think maybe 2011 or something like that. Berka theorem is 2016. So, okay, so I still have about 10 minutes. At the end, the last part, I want to basically compare to the global question. So, of course, the natural global question is basically the question of the K stability of, maybe let me draw a line here, of Fano variety. So of course, now, I mean, lots of people work on this question purely as an algebraic geometry question. So there is a large algebraic geometry theory just building on study the K stability of Fano varieties, forgetting the Caroline metric. So what are the major questions there? So the first one is I will say something like basically we just understand this notion, the K stability theory. So what for instance, what's the remaining questions here? One of the main questions is that the K stability is actually equal to the uniform version. So the uniform K stability. Of course, there is also an equivalent version for K polystability. So of course, this is a central question still left here, because we already know that the uniform K stability of Fano varieties is actually equivalent to the existence of Caroline metric for the automotive group finite case. So this is actually even known for the singular setting. So the proof for Yao-Tian-Dawson conjecture is a smooth, which for the K-stability version, which assume like a weaker algebraic geometry condition to still get this KE metric, that's only known for the smooth case. So, but in general, we expect that this is true for the singular version. But for singular version, so far, we only know you have to assume this stronger algebraic geometry condition, which is called the uniform K-stability. And then, of course, the left is a purely algebraic geometry question, which just say that the K-stability is equal to uniform K-stability. But this is still not known. So let me say this is conjecture one. Then the second part of, major part of this theory is the K moduli space. So the goal is basically once you fix the numerical invariance, we want to prove that all the K polystable Fano variety with the same numerical invariance is actually parameterized by some projective variety. So here, this projectivity is very crucial because that implies this modular space is actually compact. So actually that's a major left part. The major left part is the modular space parameterize K polystable Fano, let's say with fixed volume is proper. So basically now we already know the modular space exists and we know it's separated. Of course, to prove this, that requires a lot of work. I mean, that's work by many people, but we already know that. And the left is, the major left thing is to prove this is still proper. And actually, there is a conjecture. There is a final generation conjecture, which imply both conjecture 1 and 2. So there is a final generation type conjecture, which we know implied conjecture 1 and 2. This implication is again very non-trivial, but we already know it. So what's a final generation conjecture? So this is basically the global setting. The global setting basically says that if I consider X a Fano variety, and we assume something called a delta invariant is less or equal to 1. So this basically the equivalent to say X is not uniformly K-stable. So then the conjecture say, so first we already know all valuations over X which compute delta X are quasi-monomial. So again, we're back to the situation that we already know it's quasi-monomial. And so now let's say variation V. So then we can consider the ring, which is just given by the H0 of all the anti-canonical sections, that's M. And then we consider the gradient ring of R by this valuation, by any valuation which computes which computes the delta X. Then we want to say this R0 is finite generated. So basically this is the conjecture part. So we already know this function delta is well defined, and we know when it's less or equal to 1, it's computed by some quasi-monomial valuation. But then the conjecture is this actually valuation is a finite generated, induce a finite generation on this ring. So of course, you say this conjecture can be just compared to the This just compared to the local version, and this is just the finite generation conjecture of the minimizer. So you say somehow these two looks very much similar to each other. That I have a ring and I have a valuation. This valuation minimizes some function which coming from the K-stability theory, and then we want to know it's finite generated. Somehow, actually, we still have a difficulty to put these two conjectures into this one framework. So somehow, we don't have one statement which imply both these two conjectures. I think that somehow, if you find that statement, that might be conceptually very helpful for us to understand how to prove this conjecture. But so far, we don't have that. I mean, I think I made some attempt, but then it was disproved by Zhuang. So somehow, how to get one version to imply both these two, that's still kind of mysterious. And so, but let me just continue a little bit with this comparison to finish my talk. So basically, there is a third part of this question of this K-semi-stability is basically verify that the explicit Fano variety to be K-stable or semi-stable or polystable or whatever. So basically, I gave you a Fano variety. You want to verify whether this is K-semi-stable or not. Of course, we know this is a very hard question. I mean, historically, people spend a lot of time to basically verify some Fano varieties has some Kalan metric. So now we have this algebraic geometry approach. So in principle, we should be able to use algebraic geometry to prove lots of Fano variety to be K-stable. And that is the case. Actually, in the last, I would say, in the last 3 or 4 years, we prove lots of new examples which are K-stable using purely algebraic geometry approach. But still, this is the open-ending question. For instance, there are many hypersurface, smooth hypersurfaces. We don't know whether they are K-stable or not. So the comparison question is basically compute the normalized volume of a singularity. So basically, you know, to find the normalized volume of singularity, you have to find this K-semi-stable degeneration, the valuation which induced K-semi-stable degeneration. However, you know that the degeneration is K-semi-stable. That already is kind of the question in the global case. So somehow, in some sense, the global question, and this is for the K-semi-stable version, is embedded as a sub question of the normalized volume in the higher dimension. But I think that somehow they are very similar to each other. So in general, that's what this calculation, this finding out what's the normalized volume of a singularity is a tricky question. But sometimes we can just instead of compute, we can just estimate. This is either because somehow if you want to estimate, you just find if you want to get the upper bound, that's easy. You just find the valuation. But then for most of the time, what's useful is finding the lower bound. Then it's still somewhat tricky. So for instance, one big conjecture here is that we fix the dimension n. This is the dimension. Now we look at the set of volume of x such as dimension x is equal to n. So this is a set. We want to say this set has only a accumulation point 0. So of course, I mean the volume could become smaller and smaller and closer to 0, but we conjecture that's only accumulation point. So if you choose any positive number, if you look at all the possible volume above that number, we know it's at the most n power to n, but then we conjecture the numbers between. It's just there are just finite number between them, and this is actually open even for 3 dimension. So for 2 dimension, we know all the singularities are quotient singularity. So that volume is just the 2 power to 2 4 divided by the order of the group. But then for in the 3-dimensional case, because the classification for terminal singularity is already complicated. For the KLT, we don't even know. Then this is still not known. Okay, let me stop here. Thank you very much for your attention.
Thank you. Thank you very much for the talk. And now it's time for remarks and questions.
Are there any relationship between the 2 finite generation conjecture? I mean, the local setting and global setting. Can we deduce one from another?
No, so far we don't have a one statement which implies both of them. I mean, but as I mentioned, at some point I proposed one, but then it was disproved by Zhuang. So somehow I think finding this common, if there is one, then finding this like a common statement to imply both these 2 conjecture. I mean, although they look very similar, but if you can find one statement to imply both of them, I think that might be the step 1 to prove these 2 conjectures.
Okay, thanks.
Could I ask a question?
Sure.
I mean, are there any application of this volume to the endomorphism of varieties?
Well, I mean, we got some like a very weak one. I mean, for instance, this can be used to prove that there is no endomorphism of KLT singularities, which is degree larger than 1 and the Quasi et al. But I think that was probably no. I think that was probably no before us. But this will imply that.
Okay, thank you.
Mm-hmm.
Some other questions? Okay, there seems to be no more. So thank you very much. Thanks again.
Yeah, thank you.
And徐老师，你可以之后把那个 PDF 给我发一下吗？就是这次手写的一些东西。
OK， 我回头发给你。OK。
好的，谢谢。